Good morning, friends. I am Dr. Dwivedi, professor from Institute of Aeronautical Engineering, Hyderabad, India. I am in the process of about to complete my engineering thermodynamic course. This is the second last lecture. In this, I am going to take some questions from our question bank. This is the module 4, which is the about power cycles. In this, I will be discussing about power cycles, Otto cycles, diesel cycles, dual cycle, Brayton cycle, and the Bell-Coleman cycle. As per our syllabus, we have these 6 cycles, and these 6 cycles I will be discussing. Here, I will be taking some question from each one, and then I will be explaining. So here we have the first question is Otto cycles. What is the Otto cycle and its processes? Otto cycle is the working cycle for a spark ignition engine or the petrol engine. This cycle is also known as the constant volume heat addition. This we can see here that here we have the 4 processes. 0 to 1 is a suction process. 1 to 2 is a adiabatic compression. 2 to 3 is a constant volume or isochoric heat addition. Here heat is added. And from 3 to 4 is adiabatic expansion. 4 to 1 is heat rejection. And 1 to 0 is heat exhaust. If you see in the TS diagram also, 1 to 2 is a compression. 2 to 3 is a volume is constant. And here is the your S is constant. Delta S. Here also delta S is a constant. So these are the isentropic process. So 1 to 2 is a isentropic compression. 2 to 3 is isochoric heat addition. 3 to 4 is a isentropic expansion, and 4 to 1 is your isochoric heat rejection. So these are the 4 processes. So 1 to 2 is isentropic compression process. 2 to 3 is isochoric heat addition process. 3 to 4 is isentropic expansion process. 4 to 1 is isochoric heat rejection process. So I will go for the another question. What is power cycle? Thermodynamic cycles are broadly classified as a power and the refrigeration cycle. A power cycle or the heat engine. So power cycle means heat engine generates work using an energy source at a high temperature, while a refrigeration cycle or a heat pump provides cooling from a work input. So this is the cycle. So this is the definition of the cycle. So now I will why the diesel cycles are used. So you know the steam engines used a lot of coal, were very expensive and extremely inefficient. Big companies could afford them, while little business were struggling to keep up. By studying the thermodynamics, Diesel found that he could make a smaller internal combustion engine that would convert all heat into work. Otto cycle engine was having less compression ratio, so need to have high compression ratio to get more work done. So that was the reason. These are the reason in which way your diesel was developed. So next question is enumerate PV and the TS diagram of a diesel cycle. So you can see here the diesel cycle, there is a little difference. Only here the process 2-3 in Otto cycle it was constant volume process, but here it is a constant pressure process. So here 1 to 2 is a isentropic compression. Here 1 to 2. This is the process. It is going like this 1 to 2 process. 2 to 3 here it is a constant pressure heat addition and isobaric process. It is also called isobaric process. Then 3 to 4 is a isentropic expansion and 4 to 1 is a constant volume or isochoric heat rejection, HR, and it is a HA, addition. So it is a PV diagram which is shown here, and another is a TS diagram. So here 1 to 2 is a compression. Here work is we are giving. 2 to 3 is adiabatic. This 2 to 3 is isentropic. This constant pressure addition, heat addition. 3 to 4 is work output, that is isentropic expansion, and 4 to 1 is your constant volume heat rejection. So if you see this line and this line, they are not parallel, but in the previous one they were parallel, because this is a constant pressure line and this is the constant volume line. So please do take care of this type of situation. Next question is, why does heat addition happen at constant pressure in diesel cycle? What is the reason? So answer is this: the reason for constant pressure heat addition in a diesel cycle is that when the fuel is injected into the compressed air inside the cylinder, question of maintaining constant volume vanishes. So if we are putting some fuel inside in a constant volume, it is not possible, because it will take some time to burn. We need some time. So little expansion has to be taken at a constant pressure. So we are using the constant pressure process. We are adding more volume and igniting the mixture. So in this process, if you see here like this, so we are here this much we are adding the volume from here 1, 2, 3, V2 to V3. We are this much volume is taken for the burning of the fuel. So it is not a constant, but it is a constant volume, but it is a constant pressure process. Next question is, what is the dual cycle and the mixed cycle? So the dual combustion cycle, also known as a mixed cycle, Trinkler cycle, Selinger cycle, or the Sabathe cycle, is a thermal cycle that is combination of Otto cycle and the diesel cycle. So what happens? There is a disadvantage in the diesel cycle also, because we lose some expansion process in the diesel cycle, and in Otto cycle we are not able to ignite the properly, and also there is a compression ratio. We cannot increase the compression ratio in the Otto cycle. So a combination of Otto cycle and the diesel cycle, and they have clubbed it and they have given the name as a dual cycle, but it was made by the Trinkler, the first introduced by the Russian German engineer Gustav Trinkler, who never claimed to have developed the cycle himself. Heat is added partly at the constant volume, that is called isochoric, and partly at a constant pressure, isobaric. The significance of which is that more time is available for the fuel to completely combust. Because of lagging characteristics of fuel, this cycle is invariably used for diesel and hot spot ignition engine. It consists of 2 adiabatic and 2 constant volume and 1 constant pressure process. So dual cycle operations, we have here some processes are there. So here process 1 and 2 is isentropic. The dual cycle consists of the following operation, that is 1 to 2 is isentropic compression. Here this you can see in this diagram. Here 1 to 2. So if I see, it is going from here like this. This is the 1 to 2. It is a isentropic compression. 2 to 3 is addition of heat. This is at it is called Q1 at a constant volume process. Then we have the 3 to 4. 3 to 4 we have addition of heat at a constant pressure. So this is the Q2. It is at constant pressure. Now we have 4 to 5. It is a expansion process, isotropic expansion. And now we have the 5 to 1 is a constant volume heat rejection. So only this zone is different here. And here we have clubbed as a Otto cycle, 2 to 3, and 3 to 4 is a diesel cycle. So if you see here in the TS diagram, 1 to 2 is a adiabatic compression, 2 to 3 is a isobaric heat addition, 3 to 4 is isochoric, 2 to 3 is isochoric, 3 to 4 is isobaric, 4 to 1 is a adiabatic expansion, and 5 to 1 is a isentropic heat. It is a rejection. Isochoric heat rejection at a constant volume. V is a constant and P is a constant. So this is the operations for the dual cycle. Discuss the dual cycle. So the pressure volume diagram of actual internal combustion engine are not described well by the Otto cycle. An air standard cycle that can be made to approximate the pressure variation more closely is the air standard dual cycle. A more capable approach would be to model the combustion process in both Otto and the diesel cycle as a combination of two heat transfer process. One is the isochoric and another is the isobaric. So in the dual cycle process, only the difference lies between the heat addition. Here in the, if you see the Otto cycle, we have added the heat at the constant volume where the vertical line is there. But in the diesel, it is the horizontal line like this. This is the Otto cycle and this is the diesel cycle. But in the dual cycle, we have made the constant volume heat addition and the constant pressure heat addition. So this process is happening in the dual cycle, which is not in the both cycle. Compared to the Otto cycle, which assumes an instantaneous heat addition, that is called isochoric heat addition, heat is added partly by the constant volume and partly at a constant pressure in the dual cycle. Therefore, the advantage is that more time is available for the fuel to combust completely. On the other hand, the use of the dual cycle is slightly more complex. The thermal efficiency lies between Otto and the diesel cycle. So this thermal efficiency also lies between the Otto and the diesel cycle. So now dual cycle processes, this we have already discussed, so we will not take much time on this. Demonstrate dual cycle processes, isochoric processes, and it is called the isochoric, that is the 2 and 3 here. This is the isochoric process. Then we will see the, in this phase 2 to 3, there is a constant volume, that is the piston is at the rest, heat transferred to the air from an external source while the piston is at the rest, at the top dead center. This process is similar to the isochoric process in the Otto cycle. It is intended to represent the ignition of the fuel air mixture injected into the chamber and the subsequent rapid burning of the fuel. The pressure rises and the ratio P3 by P2 is known as the expansion ratio. So this P3 by P2 is known as the expansion ratio. Illustrate the Brayton cycle. Now I will be discussing about the Brayton cycle. Before I discuss the Brayton cycle, I will just discuss about what is the basic difference between the remaining previously 3 cycle, Otto cycle, diesel cycle and the dual cycle and the Brayton cycle. All these 4 are the power producing cycle. But first 3 are the reciprocating cycle. But this Brayton cycle is acting as a rotary cycle. And this is used for our gas turbine engines, this and the gas turbine power plants. So in this cycle, we have the adiabatic process for the compression, isobaric process for the heat addition, adiabatic process for the expansion, isobaric process for heat rejection. This you can see here that. So here this you can see in this we have this few components. First one is the compression, another is the combustion chamber, third one is the turbine. So air is entering from 1 to 2, it goes to the turbine. If you see the face of the turbine, while entering to the turbine, you have the more volume, and while leaving the turbine, you have the less volume. So from more volume to less volume, it means volume is reduced and the pressure is increased. So from 1 to 2, pressure is increasing. From 2 to 3, here we are injecting some fuel. This fuel may be burned by the torch igniter, or it may be also burned for starting by the torch igniter by the spark, but after that it will be continuously burning by its own heat From here, the temperature and the pressure is increased in the combustion chamber. It enters to the turbine a high temperature and the high pressure gases are entering to the turbine. In the turbine, if you see, the pressure and the temperature is very much lowered here, and then it is rejected. So 1 to 2 is a constant entropy or isentropic process compression. 2 to 3 is a constant pressure heat addition. 3 to 4 is a isentropic expansion, and 4 to 1 is a constant pressure heat addition. 1 to 2 in the TS diagram, 1 to 2 is a compression. This is the heat addition. 2 to 3, 3 to 4 is your power cycle or expansion, isentropic, and it is the heat rejection. It is a heat addition. So if you see here, one very different issue is there, 4 to 1. Till now we have seen that in all three cycle, Otto cycle, diesel cycle and the dual cycle, heat rejection was at a constant volume. The line was like this. But here it is a constant pressure like this. This has given a lot of advantage, and this is not possible for a cylindrical aircraft, the cylindrical engine or the piston or reciprocating engine. So for a rotary engine or the turbo engine, this we can manipulate and we can obtain this process 4 to 1. Discuss about efficiency of the Brayton or the Joule cycle. In a piston engine, instant high pressure and the temperature is observed post ignition. In gas turbine engine, continuous high pressure and the temperature persists. This cycle represents a steady state flow process of a control volume system. This cycle also known as the Joule cycle. Practical application is in the gas turbine engine or the GT engine. Mostly these are external combustion engine. In this, heat source is out of the combustion cycle. It gives much cleaner performance and cheap fuel and can be used. Initial cost is higher than the piston engine and also has a higher speed than the piston engine. It is used for ships and aircraft, not for the ground vehicle due to its high speed. Maximum temperature is significant high, so good quality of materials needed for the turbines. This engine is much bulky than the piston engine. So these are the few silent points of the Brayton cycle or the gas turbine engines. Next we will be discussing about explain the working of a Bell-Coleman cycle. So till now we have seen the Otto cycle, diesel cycle, dual cycle, Brayton cycle, and this is the fifth cycle. It is a Brayton's cycle. This is the Bell-Coleman cycle. Before this, all the four cycles were the power producing cycle. Means you will get some extra power, extra work will be done. But this cycle is reverse of that, and here we have to give some work. We have seen the Clausius statement. The Clausius has given that in the second law of thermodynamics that it is not possible to transfer the heat from lower temperature to high temperature. So if you want to cool our room, just like I am in this room, AC is fitted. So this room is, heat is extracted by the AC and it is delivering outside of the atmosphere. This is not a spontaneous process. A spontaneous process is the process which the high temperature will move towards the low. But here low temperature is moving towards the high. And that was designed by the Bell-Coleman, and he has discovered this cycle, and it is the reverse of our power generating cycles. So here compressor takes the air from the cold chamber and compresses to the high pressure. The high pressure and the high temperature air from the compressor flow to the cooler. In a cooler, heat removes from the air with the help of the cooling medium, which may be water. After cooler, low temperature and the high pressure air passes through the expander. The expander expands air to low pressure and produces work that is used for the driving of the compressor. The low pressure and the low temperature air from the expander flows through the cold chamber, where we want the cooling action to be taken place, where air absorbs the heat from the cold chamber, which is to be cooled, providing cooling effect. After absorbing heat from the cold chamber, air again flows to the compressor, and in this way the cycle is completed. Now I will discuss the processes in Bell-Coleman cycle. Here is the diagram. So here we have the PV diagram and the TS diagram. So it is the reverse of the heat engine Otto cycle, or this it is a reverse of the Brayton cycle. So 1 and 2 is a compression, 2 to 3 it is isentropic compression, 2 to 3 is your isochoric or isobaric heat rejection, 3 to 4 is isentropic expansion, 4 to 1 is heat absorption at a constant pressure. So here we have 1 to 2 is isentropic compression from P1 to P2. It is from this point to this point. Then we will have constant pressure heat rejection. It is the heat rejection. It is a heat rejection at P is equal to constant. Then we have the 3 to 4 is isentropic expansion. This is the isentropic expansion I am writing, and 4 to 1 is a constant pressure heat addition. This is the constant pressure heat addition. Okay, so just the references are Eunice Senegal, Michael A. Bowles, Thermodynamics and Engineering Approach, Tata McGraw-Hills. And any questions, you are welcome to ask. My email ID is ydvedi@gmail.com. Thank you very much for the joining. Please do like and subscribe. Till then, please wait for the next lecture. And the next lecture is the last lecture of this course, Engineering Thermodynamics.
Like, share and subscribe. Hit the bell icon for more updates.